Bright lights here. Well, I want to start by thanking you for staying. It's nothing like having the last session on the last day of a conference. So thank you very much. So I'm going to spend a few minutes telling you about some experiences that my team and I have had over the last year and a bit, looking at Spark SQL using a workload called TPC-DS. And the reason we wanted to choose this is, first of all, Spark SQL is one of the components of Spark that's still getting lots of use, and we've seen a lot of references to Spark SQL at this conference, and also to the famous TPC-H and TPC-DS benchmarks as well. So we want to do two things. One is look at the evolution of Spark SQL over a number of different versions. And we also wanted to look at a new kind of cluster configuration. Not the traditional cluster that most of us are familiar with in the Hadoop world, relatively small servers, lots of them, not so much memory. And again, to my great pleasure, I saw lots of talk at this conference, especially yesterday, about new kinds of larger servers with more cores and more memory. And so we're sort of on that same vein. And so we're going to take a look at the journey from Spark 1.5 to 2.1 and take a look at what happens when we get bigger. So, a bit of an eye chart. From this audience, I expect most of you have heard of TPC-DS, so I won't go through all the details here. But the core of it is that this is a benchmark that was created in the world of relational databases. Itself, this benchmark took about 10 years to create. And it's an interesting one. It was designed by a bunch of relational database performance engineers, and it's now been morphed into one that's more Hadoop friendly. They took away some of the requirements that are required of traditional databases, but it still has some things that make it hard to run on HDFS, for example. And so we've run largely a fully compliant environment, meaning we didn't change the queries, we didn't change the schema, we didn't break into the other rules, but we ran only the query subset. But what we did, we ran all the queries, which if you recall some of the other presentations you've seen so far, it's the case that only a subset of the queries were ever shown. We attempted every query. We weren't able to run every query, but we did attempt every query. So we started with 1 gigabyte, sort of the smallest scale factor that you can run the benchmark at. And if you go back to Spark SQL 1.5, we only managed to get 59 of the queries to work. 1.6, they got a little faster, but they didn't get any better. And then we saw in May of this year that with Spark SQL 2.0, an early driver, all of a sudden there was a couple of JIRAs, mainly related to subqueries, and poof, we've got all the 99 queries to run at single user at 1 gigabyte. So functionally, huge progress, and I know that Databricks blogged about that, a major step forward in terms of the functionality of SQL. Not that TPC-DS exercises the full functionality of SQL. There's still lots more to be added, but at least for this workload, it's complete. Now, when we scale up to 10 terabytes, then we can see that there's a few more failures. And some of them had to do with running out of resources, and we're still learning ourselves about how to tweak and tune all the little pieces. But overall, it ran pretty well. Then we started running multi-user, which is one of the TPC-DS requirements, and then we had more failures. So we're still working through all of those. But we decided that with all the progress that had been made, it was time to kind of go to the next level. And the thing that allowed us to think that we were ready for that is look at the evolution of the elapsed time. Now, you see here, there's only 49 queries represented here because only 49 of the queries would actually work across all those different versions of Spark. And you can see that as we learn more and more about the workload and the tuning of Spark, we were able to continue to improve the elapsed time as well. But overall, very significant improvement in the performance of Spark SQL over that year-plus time frame. Now, what we did learn is that when we looked at the elapsed time of the queries that ran, there was these significant pool of outliers that were dramatically longer running than the bulk of the queries. So most of the queries were actually running quite quickly. Why these outliers? For two reasons. Our analysis showed that one of them is that some of these queries were really just much tougher queries. They were accessing 2 or 3 of the fact tables, they were processing billions of rows, and so they had more work to do. But we also saw through some analysis that some of them had bad access plans, that there were still a lack of understanding, a lack of maturity in the Catalyst optimizer that didn't allow it to choose the right access plan. So that was the results of our experiments in the summer of this year. And with the Spark Technology Center, we posted some blogs and some tuning guides with our experiences with Spark 2.0. And then we said, time to get to the next level. We wanted to move up from the 10 terabyte testing that we'd done all the way up to 100 terabytes, which is the maximum size defined by the TPC-DS benchmarks. We wanted to, even though we'd been testing primarily with single user tests, we believe that the bulk of the real enterprise users of Spark SQL will want to be running with multiple concurrent SQL queries. As a result, we wanted to go to at least the 4 concurrent streams that are required by the benchmark and go beyond. Now, in the official benchmark, when you run multiple concurrent users, each user has to run all 99 queries. That is actually an atypical topology from the perspective of what real users do. They tend to run a relatively small number of concurrent users running extremely heavy queries, a moderate number of users running, let's call them medium weight queries, and typically, at least in the enterprise data warehouse space, a lot of users running more small, lightweight, short-running, call them interactive queries. And so that kind of mixed workload is not one that's yet formally defined by the benchmark. So we sometimes have to morph a benchmark like TPC-DS to run in this more compliant, more real-world fashion. But we want to go beyond 4. And we wanted to focus on these long-running queries and see what we could do to understand the root issues and, together with our colleagues in the Spark Technology Center, work on JIRAs that would improve things. Now, to build up this big cluster, we wanted to do something, as I said, different, and we wanted to use the latest technology. So together with Intel, Lenovo, and Mellanox, we put together a new kind of cluster just for the purposes of evaluating this new kind of topology. So we call it the F1, the Formula One. The idea is to evoke an image of a Formula One race car. You're not allowed to say Formula One, or I'll get in trouble with somebody. But F1 is not trademarked. So what we built is a brand new cluster. It's an actual picture of the cluster. It's about a rack and a half, 2 management nodes, 28 data nodes, each of which has got 2 sockets, 18 cores apiece, 1.5 terabytes per machine using those 64 gigabyte DIMMs, and very fast 2 terabyte NVMe SSD drives. So not the 500 megasecond SSD drives. These are capable of up to 2 gigabytes per second per drive. So very powerful cluster. And then we connected up with a 100 gigabit Ethernet switch so that we could pull all the data off the disk and then transmit it and shuffle it across the different nodes at high velocity. So we want to make sure we have lots of capability here to make things go fast. And even though we're dealing with 100 terabytes of data, over 500 billion rows, even after compression with a 3-to-1 ratio, it's still over 31 terabytes of data. We wanted to make sure we had lots of hardware to use when we're actually running these tests. So here's some gory details for those who want, right down to the levels of the frequency and all the specs. The total aggregate bandwidth on I/O was quite impressive, right? We have, in the neighborhood of, 400 and some gigabytes a second of bandwidth from the storage side, and over 12.5 gigabytes per second for the networking. And so in total, we had over 1,000 cores and 42 terabytes of RAM to store everything on over 400 terabytes of space. Now, how did we configure this? And there's going to be a paper published. One of my colleagues, Stuart Tate, is at the World of Watson this week, and he's got all the gory details of how we configure these things. So I'll just give a brief overview to make sure I stay in time. For the OS, we used a stock, bare metal Red Hat 7.2. And for our IBM Hadoop distribution, IOP, we use sort of the same best practices that we have for configuring the operating system, making sure that we've got memory management, process limits, all tuned up so that we can make good use of the hardware and we don't hit any limits. In terms of configuring the file system, we use XFS. In our experience with Red Hat 7, XFS is a very fast and reliable operating file system, and then we layer HDFS with some tuning on top of that. And then one of the things we always do when we build these kinds of new clusters, it's always good to evaluate and validate the performance characteristics of the underlying hardware. You wouldn't believe the number of times we found, kinks in cables or some disk that was not failing totally, but was not operating sort of according to spec. So for every set of components, here it's the I/O, we run an I/O test in order to validate that we're actually getting out of the system. This is before we even run anything to do with Spark. We're getting what the specs say they can. We do the same thing for the network and make sure that all the pieces are working independently the way they should. Now, for the network, we did a bunch of things in order to make full use of the fast network. Now, what was surprising, and it was a pleasant surprise, was we actually had to do nothing uniquely special for this new 100 gigabit Ethernet switch. So that was actually a really nice feature. We just plugged it in, everything worked. But we still have to do the same kind of tuning we would do for 10 gigabit Ethernet. Make sure that per port and per server tuning, make sure that things like timeouts and buffers and things like that are all set up for a lot of things going on at high velocity. And the other thing to keep in mind is when you're running these mega queries over such a big cluster, over so much data, some of the queries take hours to run. So you have to make sure that none of the underlying sockets time out and things like that. You don't want something to think that just because something is taking a long time to respond, that something's broken. So that a lot of the effort in order to get everything to work was really a function of making sure that we elongate various timeouts. You'll see that in the Spark section as well. And once again, validate the network performance to make sure that everything that you are expecting to have happen in the network is actually happening. Now, for Spark, again, when we got started, we read up on the internet, see what we could find. Then we waited for things to break. When things didn't work, we tried to make things better and faster and elongate the timeouts. And I think, these are some things that we've come up with. Coming to the various sessions at this conference, I've picked up a whole new list of magic tuning parameters to try. We only got this cluster up and running about 2 weeks ago, so I can't tell you that we've tried every combination of every parameter. And that to me is still one of the significant challenges ahead. There are just way too many parameters, and sort of figuring out the magic space for any workload in order to tune Spark up for all the different conditions, that's still a pretty high bar for a new user to start with to absorb all at once. So I think that's another thing for the Spark community to think about is how do we work to sort of auto-tune and eliminate the need for these parameters. I know for some of them there are actually auto-tune settings, but I got some advice that hasn't fully matured yet. There's still more work to do in that space as well. Now, one of the areas where we spent some time of our experiments, and you have to remember that at 100 terabytes, even with such a powerful 1,000-node cluster, there were initially lots of queries that were not finishing within an hour. So that's 1,000 cores running dedicated for a full hour, and they still weren't finishing. So a full run was taking 12 to 20 hours to try and attempt all the queries. So we had only so many experiments we could run. So we worked hard to try and figure out, well, what would be sensible, and we give it a shot, and we had to make some adjustments, but we didn't do an exhaustive search through the space. So we tried to figure out how to divide up the memory. And again, with what we read, we discovered that the executor memory, we thought that with so much memory, we could really crank it up. And when we started with things like as much as 36 gigabytes per executor. But then we really found that things were actually failing more often than when we had smaller executors. So that surprised us a little bit. And we often hit in those configurations some sort of 2 gigabyte signed int limit that seems to be fairly pervasive, and I know there's a number of JIRAs open out there to address that. So when we went back to 24 gig, that seemed to give Spark enough memory in order to actually do the heavy-duty computations it needed to do without hitting those extra limits. And when we thought about running at 24 gig, that didn't seem like it was going to use up all the memory that we had. As a result, we wanted to better understand, and this is still something that we're exploring, and I have a bit better idea now after this conference, about where exactly do we put that extra memory. So most of that is this off-heap memory, and keeping track for any other overheads in the environment. So I'm sure there's more memory we can put to good use as we learn more. But our first priority was to get as many of the queries running, period, and then worry about tuning them. So it was a kind of a conservative strategy. The other major parameter is the number of executors. And so we decided to focus on the number of cores and then divide it up by the number of concurrent Spark contexts we were running. So if you're running single user, give them all. If you're running 4 concurrent streams, divide them up. And then to make sure we try and use as much of the CPU capacity as possible, set the number of executor cores to 2 as well. And with that, we found that we were able to make what I would call good, but not excellent use of the CPU. So maybe we can gain more by tuning. I also think since we've now run some tests with 4 and even 8 concurrent streams, and we're still not able to use all the CPU, I still think there's some more software bottlenecks that we've uncovered that we can work on. So this is how we then invoked Spark in order to run the queries. Nothing particularly unusual there, I don't think. The one parameter that we thought was going to be interesting was the number of shuffle partitions. 2001 is a magic number, it turns out. So we tried on either side of that magic number, and it didn't yield the desired good results, so we went back to the default for now. Again, there's probably more learning to be done in that space. So with that, we were able to run 91 of the 99 queries to success. And there's the elapsed time distribution of the 91 that we ran. Again, similar to what we'd seen before at lower scale factors, the vast majority of the queries are actually running fairly quickly. Once again, there are some higher elapsed time queries, and keep in mind that there's 8 queries that we couldn't run. And I'll spend some time in a moment talking a little bit about the ones that we couldn't run. I think for a lot of them, if we let them run long enough, they probably would eventually complete. We just were under pressure to get a set of results in time for this conference, and we were running out of time for queries that were taking an exceptionally long time. Now, based on my long years of experience with clients, to most clients, if a query takes an unbelievably long query time, it's equivalent to not working. They don't really distinguish between broken query and query that takes 12 or 24 hours to run. Now, one of the JIRA enhancements that we've been working on in the Spark Technology Center is to detect star schemas. Now, I think everybody here knows a star schema is when you have a fact table surrounded by smaller dimension tables, and normally what you want to do is take advantage of those dimension tables to do filtering of the fact table before you move on to another fact table. Star schemas started emerging in the mid to late 80s, and all the relational database vendors, IBM DB2 included, invented algorithms in order to detect such queries. In fact, I worked on such an algorithm for the DB2 database back in that time frame. And we now have part of our engineering team applying some of those techniques from the database world and applying them to Spark. There's a nice Jira here where they have submitted a pull request for an enhancement, and you can see that at a smaller 1 terabyte scale factor, there's a significant number of queries that are quite dramatically improved by detecting the star schema. So what does this really do? Here's one example of one query. You can see up on the top right, you see the schema. You can see in bold the 3 fact tables. In the original plan, you can see that all 3 fact tables are joined early, and because they're so large, they can't be cached. As a result, you have to revert to a sort, merge, join, and the queries just take dramatically longer. If you shift over to the right, you can see that we've identified, we take the very largest of the fact tables and then join in some dimension tables, which helps shrink the intermediate result. And because they're small dimension tables, they can be cached, so you can do the hash join. You still have a large amount of data left, so the remainder of the joins with the fact tables still have to be done with a sort, merge, join. So I hope the community will take a close look at this Jira, and hopefully we'll get it into Spark SQL 2.1 or soon thereafter. So I said I was going to talk a little bit more about the queries that we could not run. Remember, I only was able to run 91 of the 99 queries. So for 4 of the queries, we had done some early testing on a subset of the cluster while we were still assembling the giant cluster. And we couldn't even get them to finish after many hours of running, even at 30 terabytes. And so for those, we looked at the plan. They looked very much like plans we'd received earlier at 10 terabytes that were just very long running queries. So we do believe they would eventually finish, but it would take, probably 12 to 24 hours to run before the queries would finish. And we have a number of other plans for Jiras in order to be able to better run those queries. One example, there's a feature in SQL called a common table expression. This is when you take a named subquery, you stick it up top, and then in most SQL engines, if they're advanced, they will, as appropriate, compute the answer to that subquery once, take that temporary result, and then reuse it wherever that common table expression is referenced. Today, in Spark SQL, we recompute the common table expression each time it's referenced. There's an extremely small set of cases where, in fact, that will be beneficial, but as a heuristic, you're much better off computing the answer once and reusing the answer multiple times. So there's an example of another Jira that we hope to get in the future. Then there was another set of queries which we let run for 1,000 core hours, and then shortly after that, it looked like it was nowhere close to finishing, and so we killed it. So again, when time permits, we'll run those and see what we can do about those. And then there was one query where we got this code 134, and I think that means we haven't configured things quite right, and we ran out of time to try another full run with all the configurations. Based on what my Google searching says, that this is something that's relatively well known. Maybe afterwards somebody can come up and tell me the magic answer to make this go away. So last few slides just to show you how the system was running. So this is what the throughput test. This is 4 concurrent users. So 4 users all trying to run the 91 queries that were working over time. So we have peak utilization of 87% of the 1,008 cores. Average was about 50%. To me, that's what I said. That's good, but not outstanding. We'd like to push it higher. And maybe some of it we can get through more tuning. Some of it I think is going to take more innovation in terms of new enhancements to Spark. In terms of the network, again, overall, we were able to make excellent use of that 100 gigabit Ethernet. Peak, we were moving, more than 58 gigabits per second through the network. So that's pretty impressive. And so I think that 100 gigabit Ethernet is really going to be a valuable piece of infrastructure for building new Spark clusters. For the I/O, again, remember we had each of the nodes had 8 drives. Each drive is capable of reading at 2 gigabytes per second, so a total maximum throughput of 16 gigabytes per second for a single node times the 28 nodes. And again, the average was more modest, but at peak, this is now looking at an individual node, we're looking at pretty significant I/O load across the cluster. So again, even though we had so much memory, even so we had done the compression into Parquet, still we were doing substantive amounts of I/O, especially you can see in some of the queries, you're getting a fair amount of write activity for the shuffles because there's very large intermediate results. So let me just wrap up by summarizing that our view is that Spark SQL 2.0 is a huge step forward. There's yet more enhancements going into 2.1. We're using just a pull from the trunk. Seems pretty stable, so we're excited about what will happen in 2.1, especially if we can get some of those JIRAs in. I think that very much like some of the other talks that have been held at this conference, there is a possibility for getting some pretty tremendous space and power savings by reimagining a cluster, moving away from this very large cluster to a smaller number of nodes that are more powerful. And Spark is evolving rapidly in order to be able to take good advantage of that new kind of hardware. TPC-DS has been mentioned a lot at this conference. It's a good workload. It exercises the I/O, the CPU, and the network. It has easy queries. It has hard queries. It's a good test of the runtime environment. It's also a good test of the evolution of the Catalyst optimizer. There's definitely some areas for improvement. I remember speaking with one client, and they're very keen on Spark and Spark SQL, but they are not yet using it in production. When I asked them why, and they said, well, when Spark SQL runs, it's great, but it doesn't always run. So they need an environment in their production environment where Spark SQL runs to completion all the time. So some people this particular client was still running everything in production on Hive, waiting for Spark SQL to mature. And one of my colleagues said, well, they'd spoken with a client, and what they did is they first tried to run it in Spark, and if it failed or if it ran too long, then they used Hive as kind of a backup method because they know it would complete eventually. So I've never heard, I thought it was interesting to use Hive as a HA method for Spark. So I think that the velocity of the improvements are what I really find impressive. If I think of how much it's come in how short a time, then I think Spark SQL is well on the path to being a very powerful production-ready environment. We're going to keep this cluster. We're going to continue to work with our partners. We'll continue to learn about it and continue to blog about our results. And with that, I want to thank you for coming at this last session, and I'm happy to take any questions that you might have.
All right, let's get some questions. And we've already got somebody on the mic there. Go.
Yeah, a question about the total amount of memory. For running a TPC-DS on 10 terabytes, you need 40 terabytes of RAM. So
100 terabytes.
100 terabytes of RAM.
Well, need is not maybe the right answer, but so first of all, it's 100 terabytes, not 10 terabytes.
Okay.
And we had available 42 terabytes of RAM. Now, would it have run with less? I'm sure it would have. In fact, one of the reasons that we chose so much is that we wanted to understand what does the performance curve look like as we reduce the memory. If you start with a small amount of memory, you can only do a theoretical projection what might happen if, in fact, you were going to have more memory. So instead, what we've done is start with a very large amount of memory, filling all the DIMM slots, and then we can boot the machine with lower amounts of memory and see what the impact is of less memory. And that's definitely in our queue to test.
Okay, so you will publish the benchmark with small memory.
Absolutely, because if you have less memory, you can use cheaper DIMMs. These are the highest priced DIMMs, so this is a Formula One configuration, not a stock car configuration.
Okay, thanks.
You're welcome.
Did you try running the test set on a different SQL engine?
I'm sorry, did you
try running the test set on a different SQL engine on the same cluster?
So the question is whether we ran it with any other SQL on Hadoop engines, and the answer is no. So, I mean, we literally only got this cluster up and running a couple of weeks ago. We were fully focused on, we started with an earlier drop of Spark 2.0, then 2.1, and a later 2.1, but it's always been Spark SQL.
I'm wondering how much such a cluster would cost.
Yeah, maybe we can have a lineup. I'm sure there's some people from Lenovo that would love to take orders.
The reason I'm asking is I would like to compare that to just having more nodes with regular hardware.
Right. So I'll answer the question and then make an extra comment on that. So the list retail price of this cluster can be yours without a discount for only $5.5 million. So that's a lot. And what are the dominant components of that? It's the ultra high density DIMMs. 64 gigabyte DIMMs are still very expensive. Secondly, those super fast 2 gigabyte a second SSD drives from Intel, the NVMe drives, are still very pricey as well. So why would we use such a configuration? One of the reasons is that these are components that are dropping in price, especially these NVMe drives. So this is sort of just like think of the early days of the UHD TVs, right? They're very pricey, and then they quickly drop. Now, an HD TV is the same price as a old-fashioned TV, or even cheaper. Secondly, we wanted to understand what that price performance curve is. Now, we did get this question from others as well, and we did a projection, not a measurement, so take what I say with a grain of salt, but we did a projection as to how many nodes we think we would need to get equivalent performance using what we would call our standard Hadoop nodes. So typically, say, 12 to 16 cores, 128 gig of RAM, and say, 16 SATA drives or something like that. And we think we would need approximately 200 nodes like that to get equivalent performance to these 30 nodes. And if you take kind of a power, maintenance, total cost of ownership, we believe that this cluster already, with its premium components today, probably has 2 times better price performance if you think about the entire environment.
Yes. Would you say now that Spark SQL is a legitimate, real analytics database engine like Outliers, as you know, from IBM, obviously? Or would you position?
Yeah, that's difficult to answer because, while compared to, let's say, the trivial SQL that you sometimes see, especially when I work with clients that come from a Hive background where there's few joins and so on, TPC-DS is a tough workload. When I compare it to the enterprise customers, the telcos, the banks, and so on, where the SQL goes on for, 15 pages, has 100 joins, and so on, I think that would still be quite a challenge for the current state of the Catalyst Optimizer. The way I answered this question for one client is I said, it's probably production ready for what I would call planned SQL, where you have a chance to evaluate the SQL if it's within the parameters that we've explored so far, and it works well, then it's probably good to run. I mean, we had no failures, no crashes or anything like it. It was stable. If it just sometimes took a very long, almost indefinite amount of time to run. So if you're running a truly ad hoc sort of ask any question you like, without the workload management, without the next phase of the cost-based optimizer and so on, I would still be cautious about using it at large data volumes with truly ad hoc queries. Sorry, it's so dark, yes. And I'm staring at the lights. I can't see if there's somebody else with another question.
Yes, is IBM planning to use any of the added tunings, like for example, like Apache Ignite or any GPUs with this cluster at some point in the future?
So, it's interesting. I mean, IBM's been interested in acceleration technologies, both GPU and FPGA. I would say that it's actually been a relatively recent development that the Spark community has really become more embracing of these acceleration technologies. And so I think that as that community feeling evolves, we're going to be able to work closely together to evaluate those. I think that there'll continue to be, I would say, some tension between the fact that in most cloud environments, they're not yet ubiquitous, And in most environments, we look at the tensor frames. It's only a subset of the work that you can push down onto the GPUs. So we're going to continue to explore that. We'll have to see exactly when it becomes a true price performance winner.
Thanks.
I have a question. Which part of hardware component you think it could be improved so you can get faster speed when you run the queries?
So I actually think that right now the biggest thing that needs improvement is the software. So we were not able to fully utilize all the hardware that we had. So I think there are some software bottlenecks, and I think there were some papers in the research track yesterday that also, I think, spoke to similar things. We're not able to sort of get all the performance out of the hardware yet. In terms of, which hardware, I think I would like to add yet more CPU. I think with more work, we'll be able to take advantage of even more CPU in the system. But that's just a speculation on my part.
And one more question. Did
Sure.
you try with the...
Yeah, let's ask this the last question, just for everybody else.
Sure. Did you try with the different file formats or maybe different compression of the Parquet when you're running the test?
So the question is whether we try different formats, and the answer is we did not. So would we have liked to try with and without compression, with, say, ORC as well? We absolutely would like to do that, but again, to try and have some good results in time for this conference, we had done lots of tests earlier with, at smaller data volumes, and we sort of picked the best of everything. So again, right now, for the current version of Spark, I think ORC with snappy compression is kind of the best balance of getting good compression and good performance. So if somebody asked me, what should I use today? What we used, which was ORC with snappy compression, would be my recommendation. Sorry, not ORC, with Parquet with snappy compression is what I would recommend.
Thank you.
So I guess that was the last question. I'll stick around, and by the way, for anyone who's coming, the meetup starts at 6:30, but I'll be around for some more questions. Thanks again.
All right, let's have one last round of applause.